Okay, so now we're working with an easier one. Yeah, in this case, we have a discrete probability room and well space, and we have x and y, which are random variables, and we know that their expected values exist, right? That's important to know, meaning that whenever they say this, it means that both the expected value of x, you know, at whenever you have the absolute value, and the expected value of y, oops, y, both are lower than infinity, meaning that their expected value exists. So the first exercise is show that this is true. The first thing we have to do with expected values is to show existence. So we first show existence. So number one is show existence. Oops. So let's do that, right? Show existence means that we have to show that this exists, right? So in this case, we're going to go with a definition. So let's do that. We know that the definition of a general expected value is going to be omega in omega, wherever we have delta x. Is that delta? No, lambda x, as with the random variable omega, times the probability of the event omega. And this will be the sum of all of them, right? So from this, we know that we can take out the lambda from the multiplication, from the product, sorry, from the sum, as it doesn't really depend on omega in this case. So we can just do the following. And we know that this is simply the expected value of the absolute value of random variable x, which we know for a fact that this exists, therefore it's lower than infinity, meaning that, meaning that at the end, the expected value of omega x exists, right? Because it's gonna be minus infinity, so it means that this, we know that this is this, oops, right? And we know that any value that is finite multiplied by any other value that's finite, in this case, is going to be lower than infinity. So we can say that this is lower than infinity, therefore the expected value of lambda x exists. Now we're going to show the actual property without the absolute values, which is the same thing actually. If you want to look at it, we just remove the absolute value. So in this case, remove the absolute values, right? So we have something like that. We remove the absolute value here as well. So we have something like this. Remove absolute value here. And we have something like so. Meaning at the end that this is delta x. And that's it, So that's it for this exercise. Pretty simple. Okay, so this one is the same as the other. It's just, yeah, same thing. So we know for a fact that the expected value of x exists, and the expected value of y also exists. So let's just try to show that the expected value of x plus y also exists. So let's do that. Let me just write here to show. To show. So we're going to write the expected value of this. Let me just copy it actually. So we don't have to write it. It's going to be equal to the sum of omegas where we have x omega plus y omega times the probability of omega. Let's remember one thing, right? We know for a fact that for any values, not even random variables, the sum of x plus y, the absolute value, is lower or equal to x plus y. This is the triangle inequality. So triangle inequality, right? Pretty simple. So this leads us to understand that if we apply this here, this is going to be lower or equal to just simply put these little guys here. Oops, just erase this. And then plus, right? Same thing. Write y here. And as you can see, we know for a fact that this is just saying the following. We know for a fact that this is, this whole thing is expected value of x, oops, right? And this is the expected value of y. And we know for a fact that we can also apply these. So if we sum two things that are less than infinity, then whatever it is, this will also be lower than infinity. So we can conclude that this is lower than infinity. And we have shown that the expected value of x plus y is lower than infinity. Therefore, the expected value of ex plus y exists. Okay, now let's go for the second part, which is just showing the property, which is this guy. So let's do that. We know for a fact that this is equal to, right, x omega plus y omega times multiplication of this. This is an omega. Obviously, we have to multiply this guy. Well, this hold on. This multiplies this one and this one, so we can do two sums, right? Sorry for the burp. I just had some coffee and it's like, kind of weird. And plus, this is going to be y. No, we know for a fact that this is going to be ex plus ey, so we can just rewrite this. And basically we're done with the proof. That's pretty much what we needed to do. Rightfully so. So yeah, that is B. Okay, so we're gonna work with this one now. It states that if x is lower than y, then x omega is also lower than y omega for all omegas and omega. We have to prove using A and B that, well, the expected value of x and expected value is lower than expected value of y. So the first thing I want to do is show existence as per usual. So what we do normally is, first of all, we show the existence of these type of variables. So let's just go ahead. So the existence, let's just take x and y, x lower than y, meaning we can put this as such. Y minus x is greater than 0, right? We'll just move this x to the other side. And we take the expected value of this side, and we want to prove existence, so we use absolute value. And this is going to be simply the expected value of x. We have the triangle inequality, obviously. We know for a fact that the triangle inequality says, oops, y minus x is lower equal to y minus x. Thus, if we apply it to the triangle inequality, to the expected value, it's going to be something like so. Thus, we know that these are lower than infinity. Thus, we can say that this is lower than infinity. Thus, we can say that e of y minus x is lower than infinity, meaning that this bad boy exists. That's pretty it. Now we want to prove that this is true. So we go back. It's really not hard. We have this. So we apply the expected values. Yeah. Which this does exist, right? We know that these exist. So now we can just simply move it back. So we can see that this is true. So that's our proof. That's pretty much how you prove C. Okay, so we're gonna work with this one, which states the following. It says we have a random variable x with omega for all omegas and omegas, and we want to show the expected value of x is equal to this, right? So it's not that difficult. We just have to understand the following. So let's start first with a normal definition of our expected value, which is given as omega, and we say x omega times the probability of getting the event of omega. And this is equal, right, to this, to the following when we have a discrete probability. So in this case, we're going to do k equals to 0. K times probability of x equals to k. Then they're telling us that k is equal to this. So let's put it in there. Right? Let's put it, duplicate this, duplicate that. And we can do n equals 1, and we have the following. Now, we want to change the order, right? So it's easier to compute, because as you can see, basically, we just want to do this. We just want to simply remove this. So how can we do this? Well, simply put, we only take, we can swap them, right? As the sums are always going to be positive. The result of the sums are going to be positive. So meaning this, we can always swap them. So let's do that. Now, another thing that we have to start is, well, we are starting from n, right? From n points. So it's important to say that this is no longer equal to 0, rather n, right? So that's the first thing we have to do. And if we see the structure, this seems more like, okay, starting from n, right? What's the probability of us getting that equal to k? Well, that's simply the definition of the CDF, or x greater than n. That's simply the CDF. So we can put it there. So we get this. And then we add this guy over here. And as you can see, we are done with the exercise. We have gotten what we wanted. So that's pretty much it. So yeah.